Oh, you do
It'll be
hair?
nice that I know everybody already and I know that I get along with them.
Yeah, we
so
can
it'd
make
be
that.
nice to not have to worry about dealing with annoying coworkers.
I really didn't want to take summer classes, but I really don't like writing, so
Yeah.
I'm gonna take out a writing class that way I don't have to later. My senior year is gonna be empty, so I thought about pushing it off to there, but
Yeah. Alright.
yes.
Oh, wait. Hold on a second.
Oh my god, I'm so impressed to see kids that are in high school and taking college courses. That's nuts. That's pretty awesome.
It's fun and hard intense. Like,
Yeah.
writing and chemistry, or no, it's really good at math, so I love math.
Yeah, I didn't
Science
think I
and
like
calculator.
math very much, and now that
And I
I'm
still
back
forgot to
in
bring
school,
it.
back in school,
Although I guess if we're just doing lecture, we'll
I
probably.
like I didn't think I was into the sciences, I really dig it.
Yeah.
It's, you know, sometimes it kind of takes like a certain era of your life for things to like be fascinating, I suppose. What did I do wrong here? Oh, I'm glad I got this out of the way.
But I did 121 and I was like, this is good, I'm never doing this again. Because
You just
I
gotta
want
go.
to take 22 too for what I want to do.
What do you wanna do?
I want to be a pilot, but like, I don't know why my advisor says to, so.
Yeah, just
I
like
could never.
commercial airline pilots are paid like minimum wage, kind of not so you smart about which pilot you decide to be.
Some of them get paid really good.
Yeah,
Some of them
sure.
are like, don't get paid a lot at all.
Yeah, I feel like there was a golden age where if you became a pilot, like you got it.
Right now, they do pilots, so like some places you get a $200,000.
Yeah, because all the people that are pilots right now are like retirement age, and they're all like, okay, time for me to retire, and nobody's replacing them.
It's crazy.
Yeah.
Some of them
Definitely work out a good deal.
Ask you a question about
300
this.
an hour.
So I got this one wrong, but I'm still, I guess I'm not
Yeah,
understanding,
that's crazy
so.
though.
Starting out, I think.
With the products are higher in energy, right? So this kind of thing on
At
the
this point, I'm
graph.
good with anything.
That means that you
above
had to
minimum
put
wage.
energy into your products overall, so then it was endothermic. Right, because exothermic is when the products
I
are
was-
lower. 'Cause-
I was
yeah.
seeing it differently. I was thinking that like
Is basically-
the energy it took to break the bonds was,
That's what really made me excited. Like,
it took less energy to break bonds than it took to form them, I guess, like, because when,
Yeah, oh yeah, that'd be awesome. I had a friend that wanted to be a flight
I
attendant.
understand what you're saying. I'm trying to figure
Then
out
she
how,
realized that she
I know that it's a
interacted
little
with
bit
people,
different
she's
from
like,
how I
"Never mind,
read
don't
it.
want
I'm
that."
gonna have to think about that, I think.
Yeah,
Okay, thank you.
we can also chat after class.
Yeah, maybe I'll chat over you.
At the airport right now, and she's 17, and she actually gets to go and fly the plane, and she's getting her pilot license. Are you
That's
doing that
awesome.
too?
That's what, yeah, I did one flight, and like, he let me fly everything, which is good stuff.
I was gonna say, it's so cool, I'm so jealous. She'll send me pictures of like her plane.
My stepdad and his best friends went to Vegas a few years ago, and speaking of flights, there's something flying around out there. That's like the third or fourth time that thing's looping around. Anyways, they went to Vegas and they did the dog fights, where you got to sit in the back of the plane, and they did like all sorts of loops. And he said that his friend got out of the plane and immediately vomited onto the pavement. But they got a video of it. I can't remember if it was posted it or not.
What's your friend's name?
Bailey. She's 16.
Oh, no, I don't know.
She goes on and flies all the time. She's so fun. She's doing her solo one tomorrow.
I wanna like be
All right, happy Wednesday. So did everybody enjoy their long weekend?
I got sunburned.
Yes, that's good, I think, right? Still getting your vitamin D in. And so a few of you have already mentioned that you got to slip out early for whatever, that's fine. So make sure you grab today's take-home quiz so you can give it to me next week. And then, of course, the homework. So that's all I have today. So we'll be lecturing the whole time just on our solution chapter. And so let's just dive right in. Do we have any questions about anything? I feel like we're all on track in this class, so I feel pretty good about y'all. All right, so let's just get with it. And so solutions, so we can think back to like homogeneous mixtures. And so, right, we can mix table salt in water or other compounds in water. And we've gotten a good taste of this in lab, right? You work with a lot of aqueous reagents. So meaning things are dissolved in water. And so, of course, right, these homogeneous solutions or homogeneous mixtures are called solutions. And then minor definition things. So the minor component, so basically what you're dissolving, is our solute. So you could add that. So what you are dissolving. And it's usually the minor component, since there's usually less. That being said, you know, I'm sure you can find exceptions to this. And then the major component is called the solvent. And for our purposes, we're mainly working with water as our solvent. If we go on to like organic chemistry, you can have a bunch of other things, right? Benzene, ether, pentane, toluene, blah, blah, blah. We won't go listing them all. And so now let's look at different types of mixtures, and so special mixtures. And so these are called colloidal mixtures. And so colloidal just means that they have large enough particles to scatter light. And so sometimes you can also synthesize these colloidal mixtures when making like nanoparticles and kind of controlling for the size. And so this gives the Tyndall effect, and that can make our colloidal mixtures appear cloudy or opaque. And so this is just like a fancy word for the most part. And so if I don't like this picture just because we can't really appreciate it. And
Like fruit punch.
but then what's even cooler, so yeah, it looks like fruit punch, but if we were actually like holding this in our lab here, it would be all like shiny, right? And all the little gold particles in there would be like reflecting light, and that'd be really nice and sparkly. And yeah, I mean, we like shiny things as humans, so it'd be really pretty. And again, that's what defines the Tyndall effect, that it's scattering the light, so they're large enough that they catch the light and reflect it and look shiny. And then we have other kind of colloidal mixtures, which I'm sure you're familiar with. And so we can look at either gas and liquid, so kind of fog or clouds. And again, think about how it's hard to tell like where the direction of the light is coming from, right? If it's foggy, then you just kind of see this weird scattered light. So same sort of effect. Or we can look at a gas-solid mixture. And I always think about like, you know, if you're maybe cleaning the cushions and then you smack them and all the dust flies up and then the light streaming in from the window and the dust kind of shines. So that's that same effect there. So all those particles shining, or, you know, of course if you smoke, but I think many of you are young in here and probably don't smoke, but right, same sort of effect. You blow some smoke and it scatters the light. And so then we have other mixtures that would also be considered colloidal. So liquid gas, like whipped cream or shaving cream. Liquid, so like mayonnaise, for example, is another Tyndall effect, and also an emulsion. And then, of course, paint, so that makes sense, right? All their coloration is from compounds. Same thing, so then we could go liquid solids. So now this would be like oil-based paints, again, those pigments and any other colorations. And then other mixtures, so we can also have like solid gas, and so that would be considered like your pumice stone, of course, leaving behind the little holes. or styrofoam is pretty light. Solid liquid, so that would be like gelatin, and again, right, gelatin's opaque. You can flavor it with a bunch of different colors and mixtures. Cheese is also considered a mixture. And then solid, so that would be like your gemstones, so a lot of their colors from impurities anyways. All right, so that's just kind of giving us an example of our colloidal mixtures. And so now we'll get into solubility. And so we get into this whole like dissolves like. And so let's kind of consider something. And so let's think about what happens if you try to dissolve salt in water versus sugar. And so what do you notice? What have you noticed when you do it at home or in lab? Which one do you think is more soluble, and maybe why?
Sugar is because it's more porous, isn't it? It's like a plant, so it sucks up water better than salt.
No. You gotta make some more rock candy. Because right, so the thing with the sugar is usually you have to kind of work it in, right? Like even if you put some sugar in your tea, right? Like you're trying to make iced tea. I don't know, people make iced tea here from the South, so right, you got to make sweet iced tea. But then the problem with that is you can't just dump it into your iced tea, right? Because you put your sugar in and then it just kind of looks at you at the bottom. So, you know, either you have to have your simple syrup already prepared to make proper iced tea, or, you know, mix it in while it's hot. Why is that? What is it getting at? Well, let's just think about before we move on. Well, what's the difference between salt and sugar?
Salt is
So it
It's
is,
an ion?
yeah, so it's more polar, so it's an ionic compound. Versus, so what's,
A polar covalent.
yeah, so polar covalent. So, sorry? It would probably be polar covalent. So let's look up sugar. Because sugar, right, it has C12H22O. So there's some oxygens in there. Oops. Well, that's correct, right? So it's not ionic, so it is covalent, but I still would put it in probably the polar covalent. So we do have, right, at least some OH groups. So arguably some hydrogen bonding could even occur potentially. But yeah, it's still large, so it's a molecule. So that's starting to get at the distinction, right? So one's ionic, and then the other is our covalent molecule. And so we kind of have this like dissolves like, and so what this means, and so now we can say, well, nonpolar dissolves nonpolar. Since they are similar, so they would be kind of miscible. And so again, I would give the example of you spill a bunch of oil, and normally they would spray hexane on the floor, but like we've learned, hexane is toxic, so you want to pick something else like pentane or heptane. And then, right, then obviously polar dissolves polar. And then I'll put under there, right, miscible or immiscible. Miscible. Because they're pretty similar and related concepts of whether things are immiscible or not. And so let's think about what happens when our solute dissolves. And I actually have molecules for this. And so you can pass them around too, and we can play with them. And so basically what we're thinking about, so we have, right, our little ionic compound here. And the little one is our cation, the bigger one is our anion. And of course they're attracted, right? So then this is our solute-solute interactions here. And so that's what's shown here, right? Solute, solute, so basically our intermolecular forces, or in this case, right, if it's ionic, then we kind of have our crystal lattice energy, which we didn't fully get into this class, right? But basically, we're saying our Q1, so charge 1 times our other charge, so basically more charge, better, divided by our distance. So we're just kind of keeping this in mind. So that's telling us how attracted they are. And then, so then our little water molecule comes along. And then, of course, right, our oxygen is going to be attracted to our cation. And so it's going to start kind of surrounding it. And it can kind of start pulling at it. So same thing. Now the hydrogen is attracted to our anion. So it's going to start kind of encapsulating and nucleating it. And so there's, right, your solvent-solute interactions. So this could be H2O with your salt there. And then so the question is, can these solvent-solute interactions, are they strong enough to completely break apart and then solubilize your molecule? And so, of course, right, we're looking at the most extreme as well with the ionic compound. And just like we mentioned, right, they're actually discrete charges of a cation and anion. All right, so I'll kind of pass those around so you can kind of play with them. They might move around. And so again, right, that's basically the gist of it. So again, right, we're calculating, okay, we have our solute-solute interactions. In the ionic compound, we're thinking about charges. If we're talking about a molecule, right, you're thinking about those intermolecular forces, the van der Waal, right, the dipole-dipole hydrogen bonding. So all those things come into play. And then, of course, right, if it's, let's just say, ethanol, water mixture, then you have, right, hydrogen bonding between the ethanol and the water that are kind of working to solubilize. And so that's, a lot to also think about, and, right, it's not always clear. So that's where the solubility rules come into play, right? So ultimately, we would have to run the experiment, since, again, it's not always obvious to predict, right, whether the solute-solute or solvent-solute interactions are stronger. And those magnets are pretty fun. So again, the magnets kind of really help us see the charge distribution in our water molecule, where we have our polarized end. So again, our oxygen, high electron density, indicated again by the red region, and then our hydrogens, low electron density, partial positive charge, indicated by our blue shading here. And again, play with those molecules, so that kind of helps you see that. And so as you play with them, again, you're just kind of thinking about this. So of course, right, our cation and anion were held together by our electrostatic potential charges, but it was strong, so our solvent-solute interactions were strong enough to overcome that. And so then we see now our pictorial representation of what's going around the room, right? So that's how our molecule gets solubilized, and again, our cation being surrounded by the oxygen, and then our anion totally being surrounded by our hydrogen in there. And then we can kind of think back to our light bulb. So we did the light bulb demo back in class. And so we said materials that dissolve in water to form a solution that conducts electricity are electrolytes. But what do electrolytes have to be then? What type of compound? Yeah, ionic, right? So they have to be ionic compounds, right? So they have to be something that separates into a charge. And then we'll also, so this is leading into next chapter, so we'll also learn that acids, so acids and also weak acids can be electrolytes. But I'll bring a demo that will help us show that. But it basically has to make ions, so we'll answer how the acids make ions probably next week. And so then materials that dissolve in water but do not conduct electricity were our non-electrolytes. And so I believe we saw that with our sugar in lab. And so of course, right, sugar, again, is just a molecule. So even though it's polar, and we can pull back up the structure of sugar. So yes, right, it's probably polar, we said, from all these oxygens hanging on it, but right, there's no charge, there's no cation, anion component, so it is just a discrete molecule. And so now it's just kind of showing, again, the differences on our molecular level of what's going on. And again, emphasizing that our ionic compound has a cation and anion component versus our molecule. So, right, we can still appreciate it kind of being nucleated. So it's still going to get surrounded by the water molecules, right, to get it into solution. But again, there's just no cation, anion component to it. So no way for it to disassociate. And so then electrolyte solutions, now we're getting into describing them more. And so this is part of what I was implying. And so mainly we've been focusing on our strong electrolytes. So again, our typical ionic compounds. And I'll add to that the ones that are soluble. And so hopefully you have a solubility list from lab. Otherwise, I can print out some more during the break, so that will also be useful. And so again, right, our solubility rules just kind of help tell us, okay, which ones will completely disassociate in water. And so just looking at like calcium chloride, we've seen it in lab, right? We've worked with it as a solution. We know it's aqueous because it dissolves. So that's what we mean too, right? When something is considered aqueous, so dissolved in solution. And right, we'll add to it, so water. You can just put those, yeah. Yep, so yeah, those solubility rules, if you have them, hang on to them. I'll print out more. And then, like I said, we'll touch on this more next week, but we can also have what's called these weak electrolytes, and that just means they partially disassociate. And so weak electrolytes, usually we talk about weak acids when we're talking about weak electrolytes. And a classic example is vinegar. But again, we'll kind of go into that more once we do a demo. So this is just kind of previewing here. And so then anything else, again, our typical molecules are just our non-electrolytes. All right, so more of the same, just kind of reiterating that. So again, we have our ionic substances that are strong electrolytes, fully disassociate. And then this goes back to now our definition of acids and bases and what's a strong acid and base. And so we are doing this right next week, so this is our last chapter. And so usually our strong bases, so let's just do our strong bases. So these are all our typical group 1, group 2, right? Sodium hydroxide, calcium hydroxide, potassium hydroxide, magnesium hydroxide, etc. Right, so all those are your typical bases, so they always dissociate. And then now just looking into kind of our other examples, and I think, again, we'll save this for next week, but we could still write it. So our strong acids, so your strong acids are going to be hydrochloric, nitric acid, hydroiodic, perchloric, which we don't really use, chloric, and sulfuric, so just the first one. 6.
After hydrochloride, the one right after it?
This one?
Yeah.
Nitric, so HNO3, and then hydrobromic. Okay. So those are the main ones, and then I'm just going to highlight these ones. So the perchlorates we just typically don't work with, but we'll still put them on there in case. But these are kind of the common ones. And so these are your strong acids. So these will fully disassociate. And so that's all that it means, right? Strong versus weak. It's just, does it fully disassociate? Then it's a strong acid. And if it does not, then it's a weak acid. And so then acetic acid is weak. But again, we'll kind of go back to this. So this is just introduction for next week, and will be helpful. All right. So then this is just re-emphasizing our non-electrolyte solution. So anything that is a molecule is, again, right, non-electrolyte. So that's been emphasized a lot in this chapter. And I'll do this demo next week for y'all, so we'll see this in person. So you did most of it in lab, right? You did the salt versus the dry salt versus water. I think you did sugar as well, right, in your little light bulb lab. Oh, we didn't do sugar? Okay, my bad. I'll bring some sugar to play with too. So I'll bring it as a demo, but then what we want to see is our weak electrolyte versus the strong acid. So I'll bring some of that. And so then this is where the solubility rules now comes into play, right? So we've talked about all these general things, and again, right, how our solvent has to break the solute-solute interactions, but then like we mentioned, okay, well, we can't predict that, right? So it's not always intuitive, and so it gives some example here. And we could also think about the reaction that you did, I think, last week in lab. So you had silver nitrate, and then added sodium chloride to it, and made some sort of white powder, or white precipitate, or milky looking substance. And you do our double displacement, so you get these two possibilities. And then that's where we look at our solubility rules. And so again, right, we're not going to get into all the energy of it, because that's basically just an energetics argument, and probably has something to do with the radius being really small, so they're probably held really tightly. But it doesn't matter the reason. We just need to be able to read our solubility chart and then determine, okay, silver chloride tends to be insoluble, so this is our solid. And so that's kind of, right, our key point is being able to identify what's insoluble, what's driving the reaction forward, and then just using our solubility rules. And so you probably are already getting a taste of that our silver salts tend to be insoluble. And then it mentions, and again, you can look at your solubility rules. So it mentions something that nitrates are usually always soluble. And so we've kind of seen that in lab, right? So your nitrates are used a lot with other metals to, again, get them soluble. I think we've worked with, right, iron nitrite as well, iron 3 nitrite in lab. So just kind of getting you a sense of what's going on. And then again, right, silver chloride from our solubility rules is insoluble. And then so, right, all this is emphasizing that we can't easily predict, so instead we have to base it off of experimental results. And so this is just another version of the solubility rules chart. I think yours is pretty similar, if not identical. I'll just say that you might see a few differences with like the hydroxide potentially, or sulfide. And so kind of the issue, or maybe like the sulfates, you see a little bit of discrepancies. And let's at least talk about it, but then we'll leave it. Oops, that's not what I wanted to do. And so I want to give a preview as to where the solubility rules come from. And because, right, we just have these arbitrary, you know, it is, it isn't soluble. And again, this is fine for our Gen Chem purposes, especially when we're just mixing two things and trying to predict, well, what was that precipitate that we saw? But just to give you context, so again, you have to test it. And so here it is, right? This is just from Wikipedia, so solubility in water. And there's kind of two relevant numbers. Again, for our purposes, it's a little much, but at least we can appreciate where it came from. And so, right, again, we're just saying 520 micrograms were dissolved in 100 grams of water at 50 degrees Celsius. And then you have this KSP product, but this would be relevant, you know, if you took my 200 level class, and then we would have some fun with some math with that. But otherwise, we're just kind of appreciating that's where it comes from. And then, you know, with different substances, if it's kind of on that line of being more soluble, that's where you get discrepancies. Let me see if I can pull up kind of another, can't spell apparently. And so magnesium hydroxide is one of those ones, it's generally considered soluble by your rules here. So you notice magnesium is not on your list. It has, right, calcium, strontium, barium, and it does mention that they're slightly soluble, so that could be confusing as well. But again, just to give it context, and so magnesium hydroxide, they say it is soluble, but then its solubility, right, is still, I wouldn't say that soluble. So 0.00064 grams and 100 milliliters, and then it gives another KSP product. And even these KSP values, I'm learning, can vary widely depending on what reference you look at. All right. But again, to summarize, you can basically just reference your chart, and that should be sufficient for this class. Does that make sense with the solubility rules and kind of, yeah, I'm trying to explain kind of where they come from just so they don't seem like crazy magic rules, but, you know, at the same time, we can just read them, appreciate them, And then just look at the general trends, you know, like all our group 1s tend to be soluble. Ammonium salts are soluble. Look at those nitrates, always soluble. Same thing with acetates. And then these are generally always insoluble, again, unless they're with the group 1s, so kind of see that. All right, let's do a little practice now. See if I can show everything. So see if you can predict whether those will be soluble, insoluble, just based off of your solubility chart. Oh, what happened to my computer? right. Are we ready to give some guesses? What do we get for our lead chloride or lead 2 chloride? Soluble, insoluble? Yeah, insoluble. That's what I like. So, right, we can look at our rules here. So, insoluble. And then heavy metals just tend to be insoluble, although what a heavy metal is by definition isn't quite clear, but we won't get into that. What about copper chloride?
Insoluble.
Insoluble?
Soluble.
Yeah, soluble. So it should be soluble. And so, right, it's not on our list of exceptions. So we do have silver on there, but yeah, copper should be fine. And if you can think back to lab, right, you,
It's on our list.
as what?
An exception to,
Oh, as insoluble?
yeah, well, copper,
Oh,
on
interesting.
it says all common chlorides are soluble, and then it says exceptions, and copper is part of the exception.
Oh,
Only copper was like one.
Nate, let me look at your rule. Oh, yeah, I think that's supposed to be copper 1 plus, but not confused. Let me look at my, let me try to find it.
Because this one would be copper 2, right? That's why it's Cl2.
Yeah, I think it's supposed to be just copper 1 on the chart, but that one, that is a little tricky. So it should be soluble. I'll put copper 1 plus is insoluble. Although, yeah, for us, we won't see probably a lot of copper 1. And then what about calcium nitrate? So soluble. So that looks good, right? No exceptions to our nitrate. And then our last one, what about barium sulfate? So insoluble. That sounds good. So barium tends to be insoluble. Questions about that one? All right, so let's keep looking. And so again, this is telling us, right, what we generally know. And I think most people kind of know this, right, intuitively. So usually if you want to dissolve something, you add heat, right, so you heat it up. And generally that works well, right? So generally that works to kind of decrease your solute-solute interactions, start breaking those intermolecular forces, right, weakening them a little bit. And so that generally helps to solubilize. And so it mentions that, right, blah, 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 most solids, right, the solubility increases with temperature. You saw that as well with the ammonium chloride. And so that's where it mentions, right, the change in heat then of dissolving is usually endothermic. But we just wanted to point out that while this is true for a majority of compounds, there are exceptions, such as cesium sulfate is kind of one of the famous notable exceptions. And we'd have to dive into the literature further on, why this is, but just something about the higher temperatures, does not actually solubilize it, and this must have like a strong interaction there. So it has to do something right with the cesium sulfate interaction. But again, that's an exception. I think most people kind of know that. So again, just kind of be aware that there are exceptions. And then the solubility curve, so all this is saying, right, if we're right on the curve, then we're right there at a perfectly saturated solution. And then if you're above, then you're supersaturated. If you're under, right, then you're unsaturated and could add more to it. And so again, just key takeaway, saturated is just right on the line. Then you compare. And so then what's kind of interesting and feels less intuitive is that gases are the opposite. So I kind of put this as like gases, opposite of solids. And so basically gases are less soluble than at higher temperatures. And so we kind of have to think about, well, what is going on that makes it that way? And so usually our gases are nonpolar molecules, right? So they're not very soluble to begin with. And then for gases, the solubility of our gas decreases with our temperature increase. So right, that would just cause it to kind of leave our soda. And then I guess we could get into debates over how best to serve soda, but just observationally, right? So if you're pouring out cold soda, it appears kind of less fizzy just because your CO2 is still dissolved in there, versus if you pour like warm soda out, it's kind of all bubbly and fizzy since that CO2 is escaping more once you've released your can pressure. And so of course, right, how can we make our solvent hold more solute? And so we can either vary the temperature, so again, thinking back to more solid things, or, you know, maybe the pressure, so now thinking about how they can under pressure. And then this also goes into kind of playing with the sodium acetate crystal in lab. You know, that was kind of a funky compound, but you could kind of play with it. And of course, it was right on that edge of being saturated, supersaturated for that sodium acetate. So that's where you could kind of crystallize it out just by pouring it. And you can also like look up fun videos on YouTube, right, if you get bored too, of things being right on that limit of supersaturated, and then you kind of hit it and it all like crystallizes. So that's why that is. And then our supersaturated solutions, again, they can be unstable when they are disturbed. So either they're going to crystallize, or in the case of our carbonated beverage, you know, you shake it, you disturb it, and then now all the gas is going to come out of solution. And then, so kind of the key point of this chapter too is dimensional analysis. And so, right, we just have another equation here, but let's break this down to kind of see what it is, and right, it's not that complicated. So we have our solubility of our gas, and then this is just given in molarity. And then it's based off of this Henry's law constant. But right, this Henry's law constant has to be found, or you know, you have to look it up for every gas. So that's kind of the first key point. But let's look at the units. So it says our Henry's law constant for CO2 at 25 degrees Celsius is 3.4 times 10 to the negative 2. And then watch those units, right? Molarity per atmosphere. And so basically, right, that's our relationship. So we can figure out, you know, how much pressure we have to pressurize and can our soda at then to get whatever desired solubility. So does that kind of make sense from our dimensional analysis? So then we'll just be plugging in like a pressure, multiplying it by this constant, then that gives us, again, solubility back out in molarity. And right, pressure, again, it depends on the units, but given that the constant is given in ATM, that means your pressure should be in ATM. So again, just always watch those units to see what you're given, and then that really tells you kind of what to do. All right, I think this is a good spot for a little break. So let's come back, you know, 155-ish or 156 or so, And then we'll get into all the units of solubility. Yeah, I think there's a pile going.
For the energy lab, did you take this thing or
Let me see. Where was it? Oh, this?
yeah.
No.
Okay.
I'm just printing it.
Alright.
I'll say I looked it up, I tried to figure out like,
Yeah,
I couldn't find it at all. So I just did.
because ours didn't work because we mixed it wrong.
Okay.
What do you recommend that I do? Do you think I just turned in this part in blank? Because when we redid it in lab, it didn't work out, and nobody else around us knew either. So
Nobody knew. I thought people did it in your lab.
we did do it, but we did it
Yeah,
wrong.
we did do it, we did it wrong, and then we went around and asked other people, and they said they hadn't figured it out.
But did they get data? Because I think people got the right data. I just don't know if they
They
figured out.
just got the colors.
Yeah, that's all you need.
Okay.
Just steal
How
the
do
color
we-
data from somebody.
Cause, see, I got that color data right here, how it was red, the dark red, the blood red, and lighter red, and orange,
Yeah,
but then I don't.
that's what I have too.
Did you figure this out in the lab?
Okay, did you see that? With some fish board. Weird. Well, that's the wrong lab.
Oh,
That's
no wonder.
This is page 14.
It's energy?
Yeah.
Yes.
Did you get this one?
I didn't finish those yet because I didn't have the data for the table. It said that question about test tube 5, so I was like, I'll just get to that.
Or I looked it up in the heat and the iron and like, I don't know, I looked it up to explain the blood red iron thing. So how did you end up figuring that out? Because of different colors or the?
Yeah, I put that on the page behind it, like what if it goes lighter, then it's shifting left. Because it's shifting to make more reactions.
Yeah, for one, that's what I was getting to in the no shift. Since it's the base.
Oh, so the first one, yeah, no
Yeah.
shift, but then the last one, I did not get that right.
The MA,
I have a speech tomorrow.
My friend showed me,
Oh,
so here,
my oral is writing, and I present tomorrow. Oh, but
reaction
oh, that's fine. I'm not busy.
is
I'm
energy
not
for exercise.
Yeah,
Yeah, first,
I'm not
lighter.
I said endothermic.
Stuck. I don't know what direction to take. I've gotten.
I don't know, I looked it up, like the whole, experiment and everything, and I said I believe it was endothermic, from trap the heat and the iron, and they also like.
Not only do I have her speech in her class, I still have 6 minutes on it. I have my 10-minute speech in my other speech class. Sorry. So I have her oral, which is at 6 minutes long. And I have my first round of first speech class last week, 4 minutes long, just with the instructions of what was that one too. And then I have the paper itself, and then the chem.
No, you're
Like, I'm
tiny.
like, I need like, but yeah, like I need, like I told them, it's like my papers. I was like, I need to focus. I was like, unless we're doing this study. I don't know. Did you see our rough draft has to be reduced into 10 pages? Yeah. For it to count? I didn't know it was so much. But like, I'm not writing the things, but I don't know if you can do it. It's like, that's kind of like, I was using all of the sources, but like, it has to like, yeah, I didn't know myself. Apparently somebody like, and then I know it's true. Why? We just found it. Her notes. Hey guys, we should go to school. I don't know what I'm supposed to do with it. I plan to graduate and have no feelings. I'm gonna go to the graduation and I'll be like, what time is it? It's next week. So yeah, I can't do it because we have the class. Well, we don't have lab. Yeah, we have lecture at 1. Yeah, I can go from like 11 to 1. It's not that I don't want to go to bonus. It's like, you know, like, I know a couple people. You guys, you know, if you want to know people, you have to go to events, right? But I'm like, well, I don't have any friends. You sound so right. This is only social interaction. This is like us. This is only us.
It's like the Oregon team official year. I'm one of the best.
Doesn't this school printer? Gross. What? That's when you have topper sins. That's nasty. That should be one of the top songs in this history.
Is this turn into right now?
Yeah, just everything.
I tried the lab last week. Did you grade any labs last week or no?
No, I'm behind on
Okay,
grading.
no, it's
I'm
fine.
sorry.
Just wanted to make sure. Yeah.
All right, did we all make it back from break? All right, so let's keep with it since This chapter is kind of dense. And so kind of the thing to emphasize now is, right, well, we have these concentration units. And so, right, we have to be able to describe how to make our solution. And, right, we have these kind of vague terms, you know, dilute and concentrated. So this kind of gives you a qualitative description. And I usually like to say anything dilute is less than like 3 molarity, you know, kind of in general. And then concentrated probably is greater than like 6 molarity or 3, you know, kind of depending. I'd say that 3 to 6 range gets kind of vague. But once you get past like, you know, 6 molar, then that's considered probably more concentrated, dangerous, right? 12 molar is obviously very reactive. But that still doesn't really tell us anything. And so we have to, again, go by our concentration. And so this is kind of what I call our cheat sheet for this chapter. But then what's kind of, you know, I don't want people to get overwhelmed, I guess, by all these different units. But we just basically always need to pay attention to our units. And then we'll, you know, do some examples. But then other things can get confusing too, like this parts by mass or parts by volume. And so what you can kind of see is you'll have various units, so it depends. Like you could do like grams per volume. So it just depends, or like weight for weight. So it could be a gram per gram solution where you're measuring both the solute and your solvent in grams. So just always pay attention to the units. So that's just kind of step 1. And so this, again, gives the overview of everything we're going to kind of talk about. So this is a good reference sheet, but then we'll go through everything in detail. And let's just dive into it. And so this one, again, preparing a solution. And so the other thing is it depends, right, if we're preparing it from a solid or whether we're doing a dilution. And we'll go over the dilution formula in a second. And so now let's see what they're trying to prepare. And so this is going to be, right, a weight per volume solution. And so they want to prepare 500 milliliters of 5 grams in 100 milliliters. And so the first step is just, of course, to calculate, right, how much do we need? And so again, this is just giving an example. And to me, this is confusing because in the example, they jump around from the units, but just pay attention. So, right, this is grams per volume. So this is a gram per, right, mass per volume unit. But then what they're showing here, 5% by mass, so that's weight per weight. So if it's weight per weight or by mass, then you're saying you have 5 grams of solute in 100 grams of solution. And then just quick sanity check, right, that's 5%. So 5 grams over 100 grams. So that gives back your 5%. Oh, sorry. And right, so for this one, since I didn't finish the math here, you could set up, like, proportions are really nice for this part of chemistry, like if you have this ratio. So again, it depends what it's given in. But if we're given this ratio, well, I need 5 grams for every 100 milliliters, and I want 500 milliliters, then we can solve, right, for X grams to give us our correct percentage. All right, so let's look at another unit. And so this is kind of going through the technique as well. So that's what this little example is emphasizing. And so now we have a 1 molar solution, but let's define what 1 molar is. And so molarity is probably the most common unit that's used in chemistry, at least for our purposes. And so it's defined up here as well, but we'll write it again. So molarity, and then just check the spelling. So this is where the only part where it gets confusing is you have molarity, right, with an R and a capital M, and that's moles per liter, and not to be confused with molality, where they just have, right, instead of an R, it's an L, and then a tiny m. And that's moles per kilogram. So we'll revisit molality, but right now we're just looking at molarity. And so we want to make a 1 molar sodium chloride solution. So that means, right, we have 1 mole of substance for every 1 liter. And now they kind of walk us through what we're doing. And so it looks like not only are we making a 1 molar solution, but we're making 1 liter of that. So I didn't really say that. And we could set up again our proportion. Well, we're making 1 liter, so we need 1 mole of substance. And so then that's what's shown here. So that's how they knew, right, okay, well, I need 1 mole of sodium chloride. And then that's just, right, the molecular weight of sodium chloride. And then physically how you do it, so properly, you weigh out your solid first, pour that in here. Or if you were doing a dilution, same thing, you pour your concentrated reagent in here. And then usually what you'd want to do is probably fill it up about 3/4 or so first. You know, dissolve it, shake it, get it all in solution. And then once it's fully dissolved, then take it to the mark, and then that's accurate. And so the other thing, right, is these are volumetric flasks. And so they're only made for measuring 1 unit. So like this can literally only measure, right, 1 liter. And it is accurate for 1 liter. The volumetrics have like their error on there, so they're super accurate. But then of course, right, if you go over the line, then you have to start all over because it's inaccurate. So just kind of keep that in mind. And so if you were making this, you kind of get at eye level, drop your water in very slowly. And then once it's at the mark, then you can shake it up again so it's fully homogeneous. And then you have your 1 molar sodium chloride solution. All right, so now we'll just keep looking at the math and kind of practicing together. And so like we just saw, again, molarity is our moles per liter with our giant M. And so, right, if we have a 2 molar solution, then that means we have 2 moles of sugar for every 1 liter. Then it just scales up, right, proportionally. So if you like proportions, that could be good. Otherwise, you know, dimensional analysis is always your friend as well. So you can still use your dimensional analysis and convert, right, go from moles to grams or whatever you need to do. And so now let's look at molality. And so molality is little m. And so again, usually we don't use it for our purposes, but if you were to move into like analytical chemistry or even industry, it is considered the superior unit. And that's only because it does not vary with temperature, since it's based on mass and not volume. So it, you know, at temperatures, you can have slightly different volumes. For our purposes, right, that difference is negligible, but for maybe a more analytical application, that's where you would want molality. And so again, just write this down somewhere, or, you know, maybe you'll want to print out this little cheat sheet later, but our molality is just defined as moles of solute per kilogram of solvent. So for water, again, it's negligible. It doesn't matter since water has a density of 1 gram per milliliter. So irrelevant for water, but matters if we're using something else as a solvent. So probably we'll go through this and then look at your homework to kind of practice all these. And so like I kind of mentioned, the parts per parts can get confusing only because it can be in whatever part, right? So that's kind of what I'm trying to emphasize is you have to just pay attention and make sure that you're in whatever units. And if it's mass, right, it could be grams per gram like we saw, kilograms per kilograms, pound per pound, or it could be mass per volume, right? Grams per milliliter, kilograms per liter, pounds per gallon, whatever. So just be conscious of that. I'll add to that, right? Use proportions. So that's probably the most helpful is you have, what you're given, and then you can set up your proportion. And so what I mean by that, and this is kind of a good example here. So if we have percentage, right, this is just parts for every 100 parts of solution. So now if it's saying, well, if we have a 0.9% solution by mass, then that's equal to 0.9 grams of solute, so then this would be solute, over 100 grams of solution. And then you can set up, right, whatever your problem is. So then if you have, 250 grams of solution that you're trying to make, then you can just cross multiply, solve for x, right? So that's kind of helpful there. And so now let's get into kind of the parts per million and what this means. And so as kind of implied here, so now if we have parts per million, then this means that we have, right, amount of solute over solution times 10 to the 6 factor. And so this can be kind of confusing. And I think it's a lot easier if we think of it like this, where parts per million is equivalent to milligrams of solute over kilograms. So you're trying to get that parts per million factor, so that 10 to the 6 factor. And so what I mean by that, so milligrams, right, is 10 to the negative third. Kilograms is 10 to the third. And so there's your 10 to the 6 factor. And so right now I'll translate it again. So if we have 3 parts per million, then, right, we're saying we have 3 milligrams of our solute over, our kilogram of solution there. So that's 3 megs per kilogram. And so again, right, you can convert that and get out your parts per billion, right? 3 times 10 to the negative third over 1 times 10 to the 3. I'll just do it to prove. So 3 times 10 to the negative 3 for milligrams over our kilogram. And so, right, that gives us 3 over 10 to the 6, so there's our parts per million. So 3 over 1 times 10 to the 6. Does that make sense? The different kind of ways to write it. So 3 parts per million is equal to this, or again, giving us back to 3 over our 1 times 10 to the 6. So you would have 3 particles of solute for every 1 times 10 to the 6 of solvent. Yes, no, kind of. And so similarly, right, we have parts per billion. So this would be, right, however 1 part per 1 times 10 to the 9th. And so this is also another one that I prefer to describe in another way. And so kind of the equivalent factor for parts per billion then is micrograms per kilogram. And again, you get back out our parts per billion. So microgram is 10 to the negative 6, kilogram 10 to the 3rd. And so there's our 10 to the 9th factor. Questions on the parts per billion? And then while we're talking about it, like why we care, so if you ever look at your Medford water report, you can, kind of see these different units in play. Let's just look right, sodium, so pretty low. So sodium is measured in parts per million. So again, like that's saying we have 6.3 molecules of sodium for every 1 times 10 to the 6 molecules of water. And then kind of cool just to see how things are reported. Also, props to Medford Water, pretty good. At least, right, free of ions. So fluoride, pretty low. That's measured in parts per million. Lithium, right, also pretty low, parts per million. Let's find lead. I was looking for a billion. Oh, here we go, parts per billion and other different byproducts. So again, just kind of appreciate where we see those units. All right, so then our next one is our mole fraction, which we covered last week briefly, last week with our gases. So we can think back to partial pressure. And so that's basically what we're saying here. And so whatever our mole fraction is just defined as our mole of whatever substance we're interested in, right, over our total moles. So in this case, we just had A and B, but of course it could be A, B, C, right, A, B, C, D, however much is in your mixture. So again, just kind of thinking back to the gases, right, we said, nitrogen is 78%, and oxygen is almost 20, etc. And then our mole fraction has no units, so it's just a fraction. Or of course, right, we can go from a fraction to a percentage. So those are pretty interchangeable. So you just multiply it by 100, you have your percentage. So that's kind of, right, the quick rundown of all our concentration. Again, our key thing being look at our units. And so let's look at other problems, though, that you might encounter. So that was nice, right? So this is kind of when you're starting from more of a solid. But what if you already have a solution and you want to dilute it? And this is also kind of what the stockroom does for us a lot. And so typically, right, you order your acid or whatever, and it comes super concentrated, right, 12 molar, and then the stockroom has to take it and do a dilution. And so it's pretty nice is we just have this formula here. So our concentration, so whatever our initial set of conditions times our volume is equal to our new concentration times our new volume. And so sometimes volume can be, right, total volume or how much of our concentrated solution we need to add. And again, this is the only formula you need, so highlight it, start it, write it down. So a couple of things about this. So units don't matter, right? It just matters that the units are the same. So they could be a molarity, they could be a molality, they could be a percentage, could be anything, doesn't matter. Same thing with the volume. Doesn't matter, as long as they're consistent with one another, right? So milliliters, milliliters, liters, liters, gallon, gallon, doesn't matter. And then for some reason, I don't know why, but textbooks like to write it explicitly as this molarity unit, but I don't really like that just because it's not all inclusive. So I'll just add again, right? Units don't matter, just same on each side. So our units just have to cancel out. And so I don't know why they give it to you, this specific formula of molarity, right, when it can be used anywhere. So that's all I'm trying to say is, right, it doesn't have to be molarity. It's just textbooks give it to you like that. All right, so now let's go through kind of how this would work. And so we're the stockroom right now. And let's just say, right, either you have purchased a 10 molar stock solution of calcium chloride, or sometimes, you prepare a stock solution if you typically dilute it. And so now this is our question. Well, how much of our 10 molar stock solution do we need to make this? And so we can start setting up our formula. So, right, this is, again, what the stockroom has to do for us to prepare for lab. And so, okay, they calculate that there's 18 of y'all, and they need 3 liters total, right, to run your lab. And so we can just set this up. So I'll just be really explicit. So C1V1 is equal to C2V2. And so, again, it doesn't matter who's your initial set of conditions, who's your final. But I just want to say, well, I need 3 liters of a 0.5 molar solution. And I'm starting with a 10 molar solution. So then V2 tells us, right, how much of the 10 molar solution we need. So let's solve for that. So 3 times 0.5 divided by 10. And then I'm just being consistent with my units, so we were in liters. So then that means we have 0.15 liters for our volume, or 150 milliliters. So now we're saying, okay, I'm going to take 150 milliliters of my 10 molar stock solution, and then we're going to bring it to 3 liters. And so now that's what's going on here. And they are using a 3-liter volumetric flask. So there's our total volume, right? You're going to dilute it with water just to the appropriate volume. And so just like before, you start off. Now, my only criticism is perhaps the graduated cylinder is not the most accurate way to measure 150 milliliters, but this is always the tough part of analytical chemistry, is using the best glassware and the most accurate for the least amount of inaccuracies. But anyways, you measure your stock solution, you pour it in there first, and then you probably want to dilute it a little bit, shake it up, and then take it to the 3 liters precisely. And so they just kind of run through the math again. So that explains what's happening. Kind of questions about this process? And so again, right, your stockroom is doing this all day, every day back there, diluting acids and all the reagents for us all the time. So super handy. And if you all ever want to work in the stockroom, they tend to hire people, kind of throughout the year, but good to know, right? So this is where your CHEM104 is useful. All right, so now let's try this one. So to what volume should we dilute 0.2 liters of a 15 molar sodium hydroxide solution to obtain a 3 molar solution? see, do we get an answer already? All right, so I'll set it up and then y'all can tell me what you got, right? So we just have our C1V1 equals C2V2. And so we're trying to figure out, so we have 0.2 liters. Oops. Try to make my L a little better. That looks like 22. So 0.2 liters of a 15 molar solution. And we want 3 molars. So basically, what's our final volume? So what did y'all get? What did you say? 1 liter. And so I get the same thing, punching it out. And so yes, right, we need 1 liter total now. And so kind of watch the language. And so this will come up, I think, on a quiz. Oh, no, it'll be next week's quiz, sorry. But basically, right, so this one is saying to what volume. So it's implying, right, total volume. So that's why this worked. So this is always giving you, like, your total volume. But sometimes you might see the phrasing, like, how much should you add? And so in that case, right, we would need to add the 0.8 liters. Does that make sense? Because if we have 0.2 liters initially, and then we have to get to 1 liter total, then we say you add 0.8 liters of solution. So kind of confusing, but just show your work so I can, again, follow your logic and make sure you don't get tripped up by weird phrasings like that. Questions on this? Feeling okay? All right, so last little bit. So now we have freezing point depression and boiling point elevation. And so we'll look at these two. And so let's kind of appreciate our graph here and what's going on. And so we have our pure solvent in our blue here. And so now we can see the effects. So we want to say freezing point depression. So that means freezing point, we're looking at this line and how it changes. So our solid liquid transition. And so notice that adding stuff to it, so making a solution, again, lowers the freezing point. And so I think many of you know this just kind of because you've seen it, right? So you live in Oregon, and so they put, stuff on the roads in the winter, obviously. Although I do appreciate Oregon as well, since y'all use rocks instead of salt. So the problem with using salt is, it ends up into your freshwater system. So Oregon's very good about keeping the water pure, which I really appreciate. And so basically, again, you kind of have these constants that you would have to look up, or on an exam, right, I'm going to provide you the constant. And so what we're appreciating is our units. So we have degrees Celsius per. Now watch this, right? This is in molality. Kind of strange, but that's just what these KF units are usually given in. And so basically we're saying, right, the more concentrated our solution is, then the greater change in temperature. And so all I care about is our change in temperature, but right, again, freezing point depression, so your solution is always lower than your solvent in your freezing point. And again, so that's why it works, right? You salt the road, that lowers the freezing point, and so that means that the ice melts, right, since it's not cold. So otherwise you have to make it colder for it to freeze. So then you can drive around.
And do the rocks that they do in Oregon give the same result?
Yeah, so that would give like the same sort of effect, because all that it's doing is it's disrupting, our crystal lattice structure of the water from being formed. So it's just getting in there with like the sand and whatever, and just kind of messing it up. So now it has to go even lower to either kind of push out some of that salt and sand and stuff to get it out of the crystal lattice that it's trying to make as it solidifies. And so that's also like part of, you know, potential purification techniques is kind of lower things and try to get things to crystallize not in your matrix. And so it kind of mentions that. So again, thinking of water, since we've all seen water at all different states. And so that salt, again, just disrupts the equilibrium. And so then you have to lower the temperature to make the water molecules, again, kind of slow down enough to attach themselves. And so again, I'd provide you this information on an exam or something. The KF, I probably wouldn't make you go hunt for it. And then it's just showing the normal freezing point. So then once you find your difference, you can just subtract from that to get your new freezing point. So let's try this one. So you should be able to do it from this information. And just read the question carefully. It says, what is the freezing point of a 1.7 molality aqueous, and that's the key word, aqueous ethylene glycol solution? So what KF did you need to use for this one? Sorry, what did you say? 1.98? Oh, why'd you pick this one? So which one do we need to pick? Here, I'm gonna close the door.
Well, my first instinct was go to the 1.992 because it's ethanol, and then the ethylene.
Oh. I was curious what threw you. So I try to highlight, what was I trying to emphasize though with the aqueous?
The water.
Yeah, the water. So right, this one always throws people for some reason. So this is just our solute. And then, so usually people try to, find ethylene glycol. So I see why you picked ethanol. But yeah, the key word is our aqueous. So this is our solvent. So then we needed the KF for water. So 1.86. And then, so we have, right, our change in temperature is just equal to our KF times our molality. So now 1.86 times 1.7. So now if we do our math here, and so then we get 3 roughly, right? And so that's just our change in temperature. And of course, we know water is at 0, but we have our chart here just in case to remind us. And so now our new freezing point, right, is -3. And so I'll round it to 2 sig figs, so -3.2 degrees Celsius.
Where's the 1.7?
Oh, just from the, right, yeah. So this is just, right, your concentration of whatever solute. So it doesn't matter, you know, and I think that's probably why the problem is written that way, to confuse you, but it doesn't matter what this is, right? Could have been ethylene glycol, could have been salt, could have been sugar, could have been aspirin. It doesn't matter. It just matters the solvent and then, of course, right, the concentration, which in this case they gave it to us. And so a similar concept is boiling point elevation. And so let's look at the chart, but then we'll get into it, and then we can get back to the debate I overheard in class, and we can talk about that. And so, right, we're looking at our liquid gas line here. So again, here's our pure solvent. And then now our solution is higher, so it has a higher boiling point. And so let's think of why. And so this is for a non-volatile solute. So meaning if you add salt. So this is like the great cooking debate, and I overheard this going on in lab. So it's basically, you know, should you add your salt, you know, to your pasta before you're cooking it, after you're cooking it? I don't know if it actually makes that much of a difference, but I've heard a few arguments to it. And so again, right, if you add a non-volatile solute, so then now it kind of, if it's non-volatile, it doesn't have energy, so it's not flying out, right, with vapor pressure, so that's kind of your key. So no vapor pressure. And so then kind of the pasta debate is, well, you know, if you add your salt before boiling point elevation, that means in theory your water has to go to a slightly higher boiling point than if you left it unsalted. But then some people say that this is better because then you cook your pasta faster potentially. I don't know if it actually makes that much of a difference. So I think that's where the lab debate was going in, and people have all sorts of opinions, but it's kind of just fun to think about on whether it matters. And so again, same sort of thing. Now we're just figuring out how much higher the boiling point is. And so now let's see if we can figure this one out. Apparently they really like ethylene glycol. And so what mass of ethylene glycol must you add to 1 kilogram of water to produce a solution that boils at 105? And so again, our change in boiling point is 5 degrees Celsius. And we do need our Kb. So our Kb for water is 0.512. And I'll write that down and see if you can go from there. So how's our problem going? Does someone want to at least start kind of walking us through the steps or how far we've gotten? So just looking at this equation, what do we need to solve for, first of all?
The mass of ethylene glycol that boils at 105.
So we do need the mass, but what do we need to solve just like before we get to the mass, right? So we have this relationship, so what do we need to get first? So what did you solve for first? Because what do we have, right? So do we have the change in temperature? Yeah, so we have that, right? So our change in temperature is 5. And then, so do we have our molality though? No, so we need to solve for that, right? And then the KB is our constant. So let's just start with that step. So we have 5 is equal to 0.512 times our molality. And so let's just solve. So 5 divided by 0.512. And so now I get that I need 9.7, and I'll round it to 7. So 9.77 for our molality. And then, do y'all remember what was the definition of molality?
Moles of solute per 1 kilogram of solvent.
Perfect. So then, right, this is nice. Well, we only have 1 kilogram of water. And so now we just need to figure out moles then. We have a relationship. So again, molality is moles over kilogram. So now we can set up, well, 9.77 is equal to however many moles for my 1 kilogram. So then how many moles does that end up being? So how many moles do we need?
Just 9.77.
Yep, so then we need 9.77 moles of ethylene glycol. If I could spell ethylene glycol. And so now from here, we're basically at the home stretch. And we just need to get our molecular weight of ethylene glycol. And we could, I'll just take it kind of rounded. So 12 plus 12 plus 6 plus 32. So somewhere around 62. So then 62 times 9.77 gives us, right, 605 grams or so of ethylene glycol.
I don't understand what you just did on the calculator.
Oh.
What numbers did you enter?
So then what I did, first I just added the molecular weight, or at least roughly, of ethylene glycol. Yeah, so that was that, and then I just multiplied, so we said we had moles, so then I just multiplied our moles by our molecular weight to give us grams. Does that make sense to everybody? Oh, question?
Yeah, so when you did the molecular weight, does it matter that the molality is per kilogram when you're going into grams for your weight?
Oh, so back it up, because remember, it's moles per kilogram of what molality is, right? So we were just saying, so first you have to calculate how many moles you need per kilogram of water, right? So that's how we got the 9.77 moles of
I just meant with that 9.77, from there you went to grams.
right,
And I was
because,
just wondering if it matters that because you were in kilograms and then you multiplied it by 9.77.
right, but that's what I'm saying is they're not quite the same, right? Because this is a molality unit of moles per kilogram, but moles by itself is defined as your molecular weight in grams. So, yeah, that's why we were to go for moles. Because this is like a separate conversion, right? Because you would have to go back to it, right? Then you have to take 605 divided by 62, so that gives you moles, and then divided by the kilogram of solution gives you molality. Does that make sense? That's why we can do that. All right, so let's at least go over osmosis in our remaining amount of time. And so osmosis is just defined as our flow of solvent from a solution of low concentration to high concentration. And so I think you have seen that with cells. And so this is useful. And so we have our osmotic pressure is equal to molarity times R, which is ATM liters moles Kelvin again, times T. So, right, temperature in Kelvin. And so really, though, this is not the correct formula. And so we need to add this factor of I. And so our I is just telling us by how much it disassociates by. So basically, the osmotic pressure is related to how many particles in solution, which is related to your molarity, but let's explain. And so if we look at this, and so basically, let's kind of rewrite this. So if we have a 1 molar solution of, let's say, sugar, right? This is our non-electrolyte. And then it's I expected just basically means how many particles. And so we expect 1 molar of sugar to still be, right, 1 mole of sugar in solution. Because again, it's a non-electrolyte, it's a molecule, so it can't disassociate. And then, so if we look at sodium chloride, so if we have a 1 molar solution of sodium chloride, so then it will dissolve into 1 molar of sodium ions plus 1 molar of chloride ions. So we get a 2 molar effective solution of ions. So that's what it means by our Van Hoff factor. So right, it's splitting into 2 parts, so that's where we have our 2. So basically, right, your 1 molar of solid turns into, again, 2 moles of ions. Does that make sense? And then this measured thing just kind of means, well, you know, it doesn't perfectly always disassociate. So they're probably doing some sort of conductivity test to get this measured value. But for our purposes, we just care about the expected, right? So magnesium sulfate, again, our polyatomic ions, so we expect it to make 1 mole of magnesium 2+, and then 1 mole of sulfate ions in solution. So 2 moles total. So same thing, magnesium chloride. So right now it has 3 parts, so 1 mole of magnesium chloride goes to 1 mole of magnesium, and then 2 moles of our chloride. So 3 molarity total. And so kind of goes on. And so this would matter, like if you're calculating molarity of like electrolyte solutions, so you'd want to calculate your total ions. So just keep that in mind. And then I know we're kind of running out of time, but look at these terminology, so be familiar with them. And so chemistry uses these terms down here. If you are in biology, you might have seen these terms. So isoosmotic, basically you have the same pressure in the cell as outside. And then hypertonic means that your solution has a higher osmotic pressure. So then basically, let's just say you had a really salty diet, and then that's going to cause your red blood cells to kind of shrivel up and lose water as it tries to compensate. That could also lead to high blood pressure, right, as all your cell water is going out into your blood vessels. And then hypotonic means your solution has a lower osmotic pressure, and then that causes the cells to swell. So this is why, like, the gallon challenge and all that, like chugging, water, milk could be dangerous if you, again, chug a whole bunch and then your cells inflate to compensate, right, for that change in osmotic pressure, and then it could cause cells to, even burst in the most extreme scenario. All right, I guess we are out of time, unfortunately, as I did want to go over some of the homework. But just make sure that you try that. And then if we need to talk about anything next week, we can, or catch up on anything. I think there's some Le Chatelier principles that we should talk about. But let's aim for Monday, and we can probably go over this on Monday as well. So
What's the date of the next exam?
it's going to be on week 11, the Wednesday. So we'll review on Monday, and then Wednesday the exam. And then grab your take-home quiz, grab it. And then I will end the stream. Thank you.